Oke, kali ini saya akan baca buku Ekonomi Mikro mengenai uncertainty. Nah, langsung saja kita baca bukunya. Ini judulnya Uncertainty.
7. Uncertainty. In this chapter we explore some of the basic elements of the theory of individual behavior in uncertain situations.
Jadi di sini mengenai perilaku individu dalam situasi yang tidak pasti.
In this chapter we explore some of the basic elements of the theory of individual behavior in uncertain situations. We discuss why individuals do not like risk in the various methods: buying insurance, acquiring more information, and preserving options they may adopt to reduce it. More generally, the chapter is
Ya, jadi di sini dia akan dibahas kenapa individu tidak suka mengambil resiko dalam berbagai metode. Contohnya membeli asuransi, memperoleh informasi tambahan, dan mencari opsi yang lain. Nah, mau kita baca lagi.
More generally, the chapter is intended to provide a brief introduction to issues raised by the possibility that information may be imperfect when individuals make utility-maximizing decisions. The extensions section provides a detailed application of the concepts in this chapter to the portfolio problem, a central problem in financial economics. Whether a well-informed person can take advantage of a poorly informed person in a market transaction, asymmetric information, is a question put off until Chapter 18. Mathematical statistics. Many of the formal tools for modeling uncertainty in economic situations were originally developed in the field of mathematical statistics. Some of these tools were reviewed in Chapter 2, and in this chapter we will make a great deal of use of the concepts introduced there. Specifically, 4 statistical ideas will recur throughout this chapter.
Ya, jadi dalam chapter ini akan mempelajari ada 4 hal yang khusus dari bidang ilmu statistik.
Random variable. A random variable is a variable that records, in numerical form, the possible outcomes from some random event. Probability density function, PDF, a function f, x, that shows the probabilities associated with the possible outcomes from a random variable. Expected value of a random variable, the outcome of a random variable that will occur on average. The expected value is denoted by e, x. If psi is a discrete random variable with n outcomes, then e, x, smiley face, xf, x. If x is a continuous random variable, then e, x, equals f, sf, x, dx. Variance and standard deviation of a random variable. These concepts measure the dispersion of a random variable about its expected value. In the discrete case, var x equals c equals e f. In the continuous case, var equals c equals f x e x f dx. The standard deviation is the square root of the variance. As we shall see, all these concepts will come into play when we begin looking at the decision-making process of a person faced with a number of uncertain outcomes that can be conceptually represented by a random variable. Fair gambles and the expected utility hypothesis. A fair gamble is a specified set of prizes and associated probabilities that has an expected value of 0. For example, if you flip a coin with a friend for $1, the expected value of this gamble is 0 because e, x, equals 0.5, plus $1, plus 0.5, $1, equals 0.
Ya. Jadi di sini ada fair gambling judi yang fair dan eh, expected utility hypothesis ya. Jadi datanya di sini fair gambling ini hasilnya yang diharapkan itu adalah 0. Jadi di mana EX setengah ini kalau contohnya melemparkan koin kan koin 2 sisi, jadi setengah ditambah $1 maka 0,5 kali kurang $1.
where wins are recorded with a plus sign and losses with a minus sign. Similarly, a game that promised to pay you $10 if a coin came up heads but would cost you only $1 if it came up tails would be unfair because EX equals 0.5 plus $10 plus 0.5 $1 equals $4.50. 7.2. This game can easily be converted into a fair game, however, simply by charging you an entry fee of $4.50 for the right to play. It has long been recognized that most people would prefer not to take fair gambles. Although people may wager a few dollars on a coin flip for entertainment purposes, they would generally balk at playing a similar game whose outcome was plus $1 million or $1 million. One of the first mathematicians to study the reasons for this unwillingness to engage in fair bets was Daniel Bernoulli in the 18th century. 3. His examination of the famous St. Petersburg paradox provided the starting point for virtually all studies of the behavior of individuals in uncertain situations. St. Petersburg paradox. In this St. Petersburg paradox, the following gamble is proposed. A coin is flipped until a head appears. If a head first appears on the nth flip, the player is paid $2. This gamble has an infinite number of outcomes. A coin might be flipped from now until doomsday and never come up ahead, although the likelihood of this is small, but the first few can easily be written down. If X.
Ya, jadi katanya di sini mengenai fair gambling ya, karena dalam fair gambling pasti tidak akan ada hasil yang menang. Nah, di sini orang akhirnya menolak ya untuk bermain dalam fair gambling, dan ahli matematika yang pertama pada abad ke-18, Daniel Bernoulli, mengeluarkan sebuah teori yang berjudul St. Petersburg Paradox. Ini merupakan di mana teori ini merupakan starting point ya bagi perilaku individu pada situasi yang tidak pasti. Nah, kita baca ulang ya.
St. Petersburg paradox. In this St. Petersburg paradox, the following gamble is proposed. A coin is flipped until a head appears. If a head first appears on the nth flip, the player is paid $2. This gamble.
Ya, jadi pada St. Petersburg Paradox, gambling yang diajukan sebuah koin dilempar hingga muncul kepala. Jika kepala muncul pertama pada lemparan keberapa, pemain akan dibayar $2 pangkat N. Jadi kalau dia N-nya munculnya lemparan kelima, maka 2/5 lah kali $2 pangkat 5 lah uang yang diterimanya.
This gamble has an infinite number of outcomes. A coin might be flipped from now until doomsday and never come up ahead, although the likelihood of this is small, but the first few can easily be written down. If X represents the prize awarded when the first head appears on the th trial, then X equals $2, x equals $4, x equals $8, 0 equals $2. The probability of getting ahead for the first time on the ith trial is, it is the probabil ity of getting, I1, tails and then ahead. Hence the probabilities of the prizes given in equation 7.3 are.
Ya, jadi katanya lemparan itu 2 pangkat N. Nah, sedangkan peluang untuk memperoleh kepala pada lemparan pertama adalah setengah pangkat I. Nah, setengah pangkat I, it is the probability of getting I kurang 1 ekor dan kemudian kepala. Maka peluang untuk memperoleh hadiah pada persamaan 3 adalah setengah Pi 1, Pi 2 seperempat, Pi 3 seperdelapan, Pi N adalah 1/2 pangkat N.
Therefore, the expected value of the gamble is infinite.
Ya, oleh karena itu, nilai yang diharapkan dari gambling adalah tidak terhingga.
Some introspection, however, should convince anyone that no player would pay very much less than infinity, to take this bet. If we charged $1 billion to play the game, we would surely have no takers, despite the fact that $1 billion is still considerably less than the expected value of the game. This then is the paradox. Bernoulli's gamble is in some sense not worth its infinite expected dollar value. Expected utility. L. Bernoulli's solution to this paradox was to argue that individuals do not care directly about the dollar prizes of a gamble, rather, they respond to the utility these dollars provide. If we assume that the marginal utility of wealth decreases as wealth increases, the St. Petersburg gamble may converge to a finite expected utility value even though its expected monetary value is infinite.
Oke ya, kita lihat di sini. Expected utility.
Expected utility. L. Bernoulli's solution to this paradox was to argue that individuals do not care directly about the dollar prizes of a gamble, rather, they respond to the utility these dollars provide. If we assume that the marginal utility of wealth decreases as wealth increases, the St. Petersburg gamble may converge to a finite expected utility value even though its expected monetary value is infinite. Because the gamble only provides a finite expected utility, individuals would only be willing to pay a finite amount to play it. Example 7.1 looks at some issues related to Bernoulli's solution. Example 7.1 Bernoulli's solution to the paradox and its shortcomings. And the expected utility. Suppose, as did Bernoulli, that the utility of each prize in the St. Petersburg paradox is given by this logarithmic utility function exhibits diminishing marginal utility, I.E, U0 but U0, and the expected utility value of this game converges to a finite number. Some manipulation of this expression yields the result that the expected utility from this gam is 1.39. Therefore, an individual with this type of utility function might be willing to invest resources that otherwise yield up to 1.39 units of utility. A certain wealth of approximately $4 provides this utility, in purchasing the right to play this game. Thus, assuming that the large prizes promised by the St. Petersburg paradox encounter diminishing marginal utility permitted Bernoulli to offer a solution to the paradox. As long as there is no upper bound to the utility function, the paradox can be regenerated by redefining the gamble's prizes. For example, with the logarithmic utility function, prizes can be set as x equals e, in which case, and the expected utility from the gamble would again be infinite. Of course, the prizes in this redefined gamble are large. For example, if a head first appears on the fifth flip, a person would win E equals $79 trillion, although the probability of winning this would be only 1/2 equals 0.031. The idea that people would pay a great deal, say, trillions of dollars, to play games with small probabilities of such large prizes seems, to many observers, to be unlikely. Hence, in many respects, the St. Petersburg game remains a paradox. Query: here are two alternative solutions to the St. Petersburg paradox. For each, calculate the expected value of the original game. 1. Suppose individuals assume that any probability less than 0.01 is in fact 0. 2. Suppose that the utility from the St. Petersburg prizes is given by X. The von Neumann-Morgenstern theorem. Among many contributions relevant to Part 3 of our text, in their book The Theory of Games and Economic Behavior, John von Neumann and Oscar Morgenstern developed a mathematical foundation for Bernoulli's solution to the St. Petersburg paradox. Point 5 in PAR. Particular, they laid out basic axioms of rationality and showed that any person who is rational in this way would make choices under uncertainty as though he or she had a util ity function over money u, x, and maximized the expected value of u, x, rather than the expected value of the monetary payoff x itself. Although most of these axioms seem eminently reasonable at first glance, many important questions about their tenability have been raised. 6. We will not pursue these questions here, however. The von Neumann-Morgenstern Utility Index. To begin, suppose that there are n possible prizes that an individual might win by participating in a lottery. Let these prizes be denoted by x, 0x, and assume that these have been arranged in order of ascending desirability. Therefore, x is the least preferred prize for the individual and x is the most preferred prize. Now assign arbitrary utility numbers to these two extreme prizes. For example, it is convenient to assign, but any other pair of numbers would do equally well. 7. Using these two values of utility, the point of the von Neumann-Morgenstern theorem is to show that a reasonable way exists to assign specific utility numbers to the other prizes available. Suppose that we choose any other prize, say, x. Consider the following experiment. Ask the individual to state the probability, say, n, at which he or she would be indifferent between x, with certainty, and a gamble offering prizes of x, with probability RT, and x, with 1. New Jersey. It seems reasonable, although this is the most problematic assumption in the von Neumann-Morgenstern approach, that such a probability will exist. The individual will always be indifferent between a gamble and a provided that a high enough probability of winning the best prize is offered. It also seems likely that will be higher the more desirable x is, the better x is, the better the chance of winning x must be to get the individual to gamble. Therefore, the probability m measures how desirable the prize x is. In fact, the von Neumann-Morgenstern technique defines the utility of x as the expected utility of the gamble that the individual considers equally desirable to x. Because of our choice of scale in equation 7.9, we have, by judiciously choosing the utility numbers to be assigned to the best and worst prizes, this choice of utility We have been able to devise a scale under which the utility index attached to any other prize is simply the probability of winning the top prize in a gamble the individual regards as equivalent to the prize in question. This choice of utility indices is arbitrary. Any other two numbers could have been used to construct this utility scale, but our initial choice, equation 7.9, is a particularly convenient one.
Oke, jadi saya kurang mengerti juga apa ini. Coba kita coba mencari apa sih. Ini kita buka dulu ya. Ini coba kita cari dulu. Nah, apa sebenarnya yang dimaksud dengan cerita tadi ya, karena ya ini Saint Petersburg Paradox ya, kita cari dulu apa itu. Adalah nah ini, jadi saya stop dulu yang ini, saya cari share screen. Nah ini ya, kita lihat ini ada bahasa Indonesianya, tidak ada yang menerjemahkannya. Ya, coba kita apa itu apa Saint Petersburg Paradox dari. Nah ini ada Saint Pop. Nah kita lihat ya. Ini kita nah ini coba kita share lagi, share screen. Nah ini ya, kita baca dulu. Apa itu Saint Petersburg Paradox? Lemparan koin. Ya, barangkali nantilah disambung lagi ya. Saya akan coba lagi. Nanti ini udah cepat sekali malam ya. Terima kasih sudah menonton. Walaupun tidak ada yang nonton.